right, so does anybody want to go over any of these? Yes, thank you. Which one? I was actually, that if no one picked, I was gonna go over 12 and 15. So I'm actually gonna ignore you for a second. I want to go over 12 first. Only because you can, yeah, no, you can see 15 pretty good up there. All right, 15 says the diagram below shows a sedimentary rock sample. Which agent of erosion was most likely for shaping the particles that form this rock? So we're not looking at the whole rock. We're looking at the pieces that make up the rock. And I want you guys to take a look at those. Do those have a signature look, the pieces? What could you say about all those pieces? They're pretty round and pretty smooth. And one of the things that I've mentioned a few times is that when rocks bump and rub against each other, when they're rolling in a river, they will become smaller, smoother, and rounder. This, I will tell you, there is a question about this type of thing on the test on Friday. You gotta know the signature look for rocks that have been weathered by rivers. Rivers are small, smooth, and round. What are gravity? If I just, yeah, so if I just drop a rock, when it breaks, it's not small, smooth, and round, it's smaller, but it's sharp and jagged and angular usually. So that is something you need to know. We will put that in the review sheet by the end of today. Just curious, did you get question 12 wrong too? Yep, question 12 is basically the same thing. So again, take a look at these rocks that make up the wall. You should notice that they are all pretty round and pretty smooth. So again, going with that signature look, rocks that are round and smooth are from rivers. Any more? Yeah. 5. Which particles are the last to settle as the river's velocity decreases? Not looking at the size or not looking at these answers. What do we know will settle slow? So it says last to settle. So they're the slowest to settle. We know for size, which one settles first? Biggest settles first, smallest settles last. Then for shape, what settles first, round or flat? Round first, flat last. So that helps because we know that so last to settle, so round will always settle before flat. So we are looking, is it going to be a flattened clay particle or a flattened pebble? Now, if you remember this chart that we learned about, throwback to chapter 3 here, clay is the teeniest, tiniest particle. Pebble's a pretty big particle. So saying a clay particle means it's a tiny particle. So the very last thing to settle will be a flattened clay particle. Make sense? Thank you for asking. Any more? No? All right, well, then grab your review sheets that we were working on filling in yesterday. Yeah, I think we got the page. Yeah, it looked here, and actually this. Okay. Did we do? Gabby was the very last thing we did with the pictures. Yeah, perfect. All right, so this is the one we did. I labeled the other class. Oh, I only labeled third period. All right, so yesterday, anybody not here and need one of these? All right, so we did these review sheets. We basically yesterday got through all of the stuff you needed to know for weathering. We named the 5 agents of erosion, and we named the keywords for gravity and a few of the keywords for glaciers. So now what we need to move on to a few things you gotta know about the other agents of erosion. So let's start with wind. take a look at page 8 and 9 of your reference table and look to see what we wrote down on 8, or not your reference table, your packet. Take a look at pages 8 and 9 of your packet to see what some of those like bell ringer words were. What? Sand dunes. In fact, we even drew a picture of a sand dune. What was so important about a sand dune? Guys, take a look at pages 8 and 9. The wind goes up a sand dune. Which side of the sand dune is it going up though? The gentle. So I want you guys to draw yourself a picture of a sand dune. With this picture, I want one side to be significantly more gentle. So we're labeling this a sand dune. Notice how I've got one really gentle side and one extremely steep side. Don't make them even. Don't make it a nice little perfect triangle. I want one gentle side and one steep side. And then we're labeling the side that's gentle with the wind. You will need to know this on Thursday, that the wind goes up the gentle side. So I think I said this yesterday, but I'll say it again. I'm only putting stuff on this sheet that I know you need to know. I'm not putting any fluff on this reference or review sheet. Only the stuff that I'm testing you on. With the wind, is it sorted or unsorted? No, tell me this. What do we know about what sediments get picked up by the wind? Right. So I'm gonna put up here, typically, only small sediments. Oops, can't spell small. But, sorry. Stronger wind equals bigger sediments. So because of stronger wind, bigger sediments, what happens when the wind slows down? Drops off the big stuff. So will they be sorted or unsorted? Sorted. All right, let's do waves next. We just did waves on Monday. What was one thing that I spent most of the period talking about? No, I did not spend most of the period talking about that, but I did that. We're going to write that down. What? No, not for waves, I didn't. Guys, look back, page 19. How do I have these pages memorized? You guys can't even find them when you flip through the packet. Do you want a staple for the 10,000th time? Oh, well, see, that's why I asked, because I could have hooked you up. I got a monster stapler. See, when I ask you a question, just answer the question I ask, not the one you think I'm asking you. Sorry. Teachable moment. Long shore current or drift. Who remembers the gist of longshore current? Sediments moved along the shore in a zigzag pattern. And what were some of the other like key phrases that I said? Not Jake, someone else. Not Renee, she answered me. Not Jesse, he's answered me. Shelby's answered me too. Thanks, Brennan. Barrier Island's got another one. Nice. Barrier Island, groin. Even as simple as a beach, guys. Those are all words that if you hear those words, you think waves. Running water is going to take us a hot minute to get through. We're going to use a couple boxes for running water. Let's start with some keywords. Water goes downhill. I'm not including that on my review sheet. I don't know. Are sediments unsorted, guys? What do we know about when water picking stuff up? Renee, or not Renee. Riley, what were you going to say? You're wrong. Okay. Somebody. Speed does affect the erosion. So faster water. Faster water, bigger sediments. So that means they are sorted. Big sediments get dropped off first. But not just big. Big, round, more dense get dropped off first. All right, so what are some key features? What do rivers make? Deltas. What else? No, no. What kind of valleys? No. V. Guys, remember the word river has a V. That should help you. And the last thing is a meander. A meander is a curve in a stream. So if you hear something about a meander, I want you to be thinking of a river. Speaking of a curvy stream, I'm going to go ahead and draw myself a curvy stream. I'm going to go down, up, and back down, and then make down, up, and back down. I'm going to label this part A prime, B prime. And we'll do this part over here, C and C prime. Hopefully your curvy river looks similar to mine. Which ones are outsides of a curve? Not all the primes. Which one? Is it A or A prime is the outside of a curve if the water is going this way? I heard somebody say it. A is the outside. What is another outside? What happens on the outsides of the curve? It is more erosion. Why is there more erosion? Yes, water's faster. Faster water equals more erosion. And because there's more erosion, what's the depth? Deeper. So let's draw what it would look like if we go from A to A prime. What do you have to ask yourself when we draw these pictures? What's the first step? Not Jake. Thanks, Jake. Kelvin, you know, right? What do we ask ourselves first? No? Nate, look like you know. No? Who else wants to answer this for me? You know? You got it, not the middle, you gotta find the deepest spot. That's what you meant. I think. So you gotta find the deepest spot. How do we know where it's going to be deeper? Which part of the curve? Well, the outside of the curve is always going to be deeper. So you ask yourself, is A or A prime the outside? We already talked about this. It is A, is on the outside of a curve. So you put the deeper spot. So you just label a dot there over near A and you connect them up. So you do need, there will be several of those on the test on Friday. Gonna have to recognize what the bottom would look like. And the key is the deepest spot is always near the outside. What about on a straightaway? Let's label this if you want. Deepest spot near outside curve. What about on a straightaway, such as my C to C prime? C to C prime, it's in the middle. Deepest spot near middle on straightaway. Couple more things. Yeah, about running water. We talked about the life cycle of a stream. What are some key features? Oh, here, I see you guys are still looking. Is there, what can't you see, Kelvin? Here. This says deepest spot near middle on straightaway. Anybody else not able to see something I wrote? Everybody got that part so far? Can I move? All right. Life cycle of a stream. What does a young stream typically look like? Skinny. Has another really important feature. Straight. They start off straight. No wrinkles. Get a little wrinkly. And then they get really wrinkly when they're old. Deposition. When sediments get dropped off, we already put that on the front. Remember, sometimes they're sorted and unsorted. Will wind be sorted or unsorted? Sorted. Remember, as the wind slows down, the bigger, more dense round particles settle out first. How about waves? Sorted. And how about running water? Sorted. How about glaciers? Unsorted. How about gravity? Unsorted. 3 W's are sorted, the 2 G's are not. And I think I have told you a bazillion times glaciers are unsorted. So if you can remember that the G side is unsorted, then the other ones you don't have to think about too much.
The one we do in class, which is lab, we go by G's don't care.
Oh.
They don't sort and they don't layer.
Yeah, G's never really care about the ops.
Gravity places, they don't care. Just drop.
Perfect. I like it.
Start with the same.
The last thing is I want to talk about when a river enters a lake or an ocean. How do the sediments look when they get dropped off? This is a lot like the water slide example I talked about with my kids and my husband. You want everything. So when you have a river that enters a lake, what sediments get dropped off first? The bigger. So they will be bigger sediments at the beginning of the lake. Medium sediments a little bit deeper into the lake, followed by all the teeny tiny particles after that. I believe this review sheet has covered just about everything, except for one thing that I totally forgot to teach you. So grab your reference table, open it up to page 7. I didn't even include it in the packet. That's how much I totally forgot about this. Go into this reference table right here in the upper corner of page, I'm sorry, this is 6, not 7. I lied. Top corner of 6. We've already looked at this reference table. Yeah, sorry, reference table, your blue packet, not your regular packet. Page 6, upper right corner. We have already looked at this. If you remember what we did with this back in chapter 3. So remember chapter 3 was rocks and minerals. We talked about how big pieces of clay, silt, and sand, those were written right here on page 7. But pebbles, cobbles, and boulders, they didn't tell us how big they were. So we had to look over here to figure out how big a pebble, a cobble, or a boulder was. And you just used these dotted lines back in chapter 3. And I told you to ignore everything else until a little while from then. Well, welcome to now. This is when we got to talk about the rest of this graph. So first of all, it's just a graph. I don't want you to freak out. Just a graph. You guys know how to operate graphs. It is a relationship of transported particle size to water velocity. So how fast are rivers going? Before we even look at this graph, what happens to the size particles when a river speeds up? What else? What can it carry? Right. You already know, and we'll put this up here. Nope, you know, faster water equals bigger particles. You already know that, or bigger sediments. You already know that. And in general, you can see that on this paper when stream velocity gets faster. So when you read the X, we learned this back in chapter 1, stream velocity increases, particle diameter increases, which means the faster the water, the bigger the sediments. So you basically already know the gist of this reference table. It's nothing fancy. This is why I skipped it. It doesn't take long to figure out. So now, instead of just saying faster water, I'm going to give you a number. So instead, I could say 1 centimeter per second or 100 centimeters per second or anything in between. They're all just labeled there. And now instead of saying bigger or smaller sediments, now I'm going to give them actual sizes. 0.001 centimeter, 100 centimeters. Now I can give you an actual number. So it's nothing difficult. Still the same concept, faster water, bigger sediments, just giving it numbers. There's a couple weird things because it wouldn't be the Regents unless they made it difficult. First thing, let's look at a graph. When you guys make a graph, what are some rules for making graphs? They need a title, check. What else do graphs need when you make them? Numbers, what are the rules about the numbers or the labels? Usually when you make a graph, there has to be a nice pattern. Meaning, I think I have one here, like they gotta go up by tens. Or they gotta go up by ones. And the rule is you gotta stick with it, right? If you start labeling with a 10, you stick with 10. The other rule with numbering is they have to have a good, nice, even spacing. Well, the Regents likes to break all the rules. Take a look here. What do you notice about the spacing of the little lines?
Oh, kind of.
They're wonky. I love it. Who said it? That's what I would have said, Shelby. They're wonky. This is actually what's called an exponential graph and blah, 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 blah. Either way, if you made a graph look like this, the Regents would mark you wrong. Why they get to do it, I don't know. So first of all, the spacing's wonky. Second of all, let's look at 1 because this is the easiest place to look. 1, 5, and 10 are labeled. What are they counting by in that section where the 1 is? Everybody look at your own. You can't see mine. So each little line, yes, they labeled every 5, but what are they counting by? Yeah, 1. So here we have, I'll go here. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They fit perfectly. So what would you expect to come after 10? You'd think, right? Makes sense. Makes sense to me. So let's see. 10, 11, 12, 13, 14, 15. Why is it labeled 50? Now it's going up by 10. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Again, you'd expect then 110 to be next. Is it? What are they counting by next? Then they're counting by hundreds. So they keep switching what they're counting by. It's okay because the key is whatever they label here at like the 1 spot, here like ones, they're counting by ones. Where it's labeled 10, they're counting by tens. Where it's labeled 100, they switch to hundreds. The same is true for these little decimals. Here where they're counting, where it's labeled 0.01, the next one is 0.02. So they're going up by 0.01. Same with the 0.1. They're going by 0.1. So 0.1, 0.2, 0.3, 0.4, 0.5. So even though it's weird, it's not that bad. You just have to slow down and think. So here, let me ask you this. Otherwise, do you know how to use a graph? Like if I said, if the stream velocity is 10, what size particle can it carry? So no, hang on. If the stream velocity is 10, what size particle can it carry? So I gave you a velocity of 10. How do I figure out how big of a particle it can carry? What do I got to do? How do you read this graph then? Hang on, I gotta grab a new reference.
You go up to like those flat lines.
Yeah, perfect. That's what I was getting at. And so maybe I was just being a little confusing. So if I say the stream velocity is 10, what size particle? I go from the 10 up till I hit the black line. Yes, there's other lines. Ignore those for this. So I hit the black line and I read over. Where is that then? How fast or what size particle? It's one line after 0.1, so that's 0.2. So not bad. And then what is that, by the way? That's the biggest piece of sand you can have or the smallest pebble. So here's another thing. If the river is flowing 10 centimeters per second, what kinds of particles can it carry? Can it carry pebbles? For most pebbles, it cannot carry a pebble. Can it carry sand? Yes. Can it carry silt? Anything smaller than that biggest one, it can carry. So if it's carrying sand, it's carrying silt and clay as well. I want to do a couple of your homework questions with you right now. Make sure you see what I'm talking about. least you guys.
Oh, I got
Yeah.
one right here.
You-
Someone left it.
Oh, great. Shelby, you said you were gonna redo it, didn't you? Make,
No, I just got
oh, no worries. You have time today then, right? Lab today? Okay, so these questions are your homework. Let's get a couple of them done here. And make sure you know how to use the reference table. So it says, what is the largest particle that can be kept in motion by a stream that has a velocity of 100 centimeters per second? So what did they give us? They gave us the velocity. So yes, there's 100 listed twice. Make sure you use the right 100. They said velocity of 100. So you point to the 100, the velocity of 100. Then what should I do? Go up till you hit the line. Right here. Now, do they even ask us how big that is? They do not. They just ask what is the largest particle that stream could carry. Let's go through the questions. Can it carry silt? Yes. But is that the answer? Why not? It's not the biggest. Can it carry sand? But is that the answer? Because it's not the biggest. Can it carry a pebble? Yes. Double check, can it carry a cobble? No. So that answer, the biggest thing it could carry is a pebble. Okay, I think we got time for one more. Read the question carefully. What is the largest particle that can generally be transported by a stream moving 200 centimeters per second? I want to point something out. Well, of course I moved it. They do have the little marks up here at the top, the same as they have at the bottom. So for in this corner, where it's squished all in the corner, you can draw the line down as well, if that makes your life easier. It's the same numbers. So what do you notice about my line and the line in the boulder section? Can I carry a boulder if I'm going 200 centimeters per second? No, but how about a cobble? Yes, I can carry the cobbles. All right, wait, we got time for one more, right? Let's try one more. This is going the other way. What is the minimum rate of flow at which a stream can maintain the transportation of a pebble 1 centimeter in diameter? Does it say one? One. Which one do I use? This one or this one? How did I know I used the side one on the y-axis? Because they gave us the size 1 centimeter right here. They gave us the 1. Go over till you hit the line. Now go down. How fast is that stream? Approximately 50. It is hard to tell, was it right on the 50, but through process of elimination, it was not at the 100, and it certainly wasn't anything bigger than that. You have 10 more questions for homework. Finish that up. That is your homework. Questions 4 through 13.